So today we will talk about the acceleration due to gravity. Okay, so let us see the acceleration due to gravity due to the earth. All right, so let's suppose this is our earth and there is some object somewhere. Okay, so let's suppose there is some object over here. So r is earth's radius. Okay, r is earth's, oh sorry, r is earth's radius and h is the height of that object above the earth's surface. Mass of the object is m. Okay, mass of the object is m and mass of earth is capital M. So what would be the gravitational force acting on that object due to earth? So we know, according to Newton's universal law of gravitation, the gravitational force the gravitational force acting on that object on m due to earth is F equals to g times m multiplied by small m upon r square. Okay, distance square. And this small r is equal to this capital R plus h. Small r is equal to what? Capital R plus h. Okay, so where I can say this distance between the object and the center of earth, it is equal to r plus h. Okay, then now this force is equal to, we can say, mass times acceleration for this mass, right? Force acting on this mass m, it is equal to mass times its acceleration. Okay, so from that we can write F is equal to mass times acceleration, but this acceleration is because of the gravitational force, and that's why we'll write it as acceleration due to gravity, g. Okay, instead of common letter a. Okay, but this mass is at height h, so I will put suffix h over here. So it's acceleration due to gravity at height h above the earth's surface. Okay, so we get m times gh is equal to g multiplied by m into m upon r square, and we can cancel out this m and m. So what do we get? We get g at height h is equal to g times m upon r square, or we can substitute small r equals to capital R plus h. So it is g times m upon r plus h square. Okay, so acceleration due to gravity at height h above the earth's surface is equal to g, the universal gravitational constant, multiplied by mass of earth divided by r plus h square. Okay, where r is radius of earth, h is the height. So this is formula for acceleration due to gravity at height h. Now let's suppose h is equal to 0. Okay, so for h equals to 0, that is, now we are on earth's surface. Okay, so acceleration due to gravity on earth surface, what is it? So it is now just g. Okay, or you can say g at h equals to 0, and it is equal to, put h equals to 0 here, so we get g times m upon r square, right? So this formulae that we are going to derive, they are important. Okay, so we need to remember them, but they are easy. So now what we'll do is we'll compare acceleration due to gravity at height h to acceleration due to gravity on earth's surface, and we'll find out a relation between them. Okay, so what is acceleration due to gravity at height h? It is gm upon r square, small r square, which is capital R plus h square, right? So I can write that g at height h is equal to g times m upon r plus h whole square. Okay, and then I can divide this by this formula. Okay, so what do I get? So I will get gh upon g is equal to gm upon r plus h square, and divided by this is equal to multiplied by its reciprocal. So see, it is r square divided by gm, we can say. Okay, and then this gm and gm gets cancelled out. Okay, gm and gm gets cancelled out. So we get this relation that gh upon g is equal to r divided by r plus h whole square. Okay, we get this relation gh upon g is equal to r divided by r plus h square. Right. So then what we can do is we can move this g on the other side. So we can say gh is equal to g multiplied by r upon r plus h square. Okay. So gh is equal to g multiplied by r upon r plus h whole square. Right. So we'll memorize this formula. Okay. This one or this one, it's the same formula. Right. And then what we'll do is we'll take r common from numerator and denominator. So what do we get? So we can take r common from numerator and denominator. So if we take r common, okay, it gets cancelled out, right? So taking r common from numerator, 1 will remain there. Okay, so it is r upon, if I take r common from this term, what will happen? So it is r upon r, right? That's 1 plus h upon r, that is h upon r. Okay, so it is 1 plus h upon r is what is left, and we have square of this term. So this r and r gets cancelled. So it is 1 upon 1 plus h by r raised to 2. Okay, or you can say it is g multiplied by 1 plus h upon r raised to minus 2. Okay, it is 1 upon 1 plus h upon r raised to 2, or if you take it into the numerator, then it becomes 1 plus h upon r raised to minus 2. So is it clear till this point? Okay, so we'll find out an approximate formula for the acceleration due to gravity at height h, and for that we need to make use of a theorem which is known as binomial theorem. Okay, so you must have studied this theorem in maths, right? So it is a plus b raised to n is equal to a raised to n plus, it is n times a raised to n minus 1 multiplied by b raised to 1, okay, plus it is n times n minus 1 divided by 2 factorial, okay, multiplied by a raised to n minus 2, b raised to 2, plus so on and so forth up to plus it will be b raised to n. Okay, so this is the theorem. Okay, so using this you can write 1 plus x raised to n. Okay, and what is our x? It is h upon r. So a is 1, b is x. Okay, so it will be 1 raised to n, that is 1, plus n times, it is n times. Now a is equal to 1, so a raised to anything is 1. Okay, then b is equal to x, right? So b raised to anything. Okay, here we have b raised to 1, so it will be x raised to 1, right? X raised to 1. Okay, plus you will have n into n minus 1, n multiplied by n minus 1, upon 2 factorial multiplied by x raised to 2 plus so on and so forth. You will have up to x raised to n. Okay, so from this formula, by substituting a equals to 1 and b equals to x, you get this simplified formula. Okay, we are going to use this theorem, right? We are going to use this theorem, binomial theorem, to find out approximate value of acceleration due to gravity. Okay, so till now there is no approximation. I mean, if you substitute x equal to h upon r, okay, if you take x equals to h upon r and put n equals to minus 2, okay, it is 1 plus x raised to n. So take x equals to h by r and n equals to minus 2, right? Then expand like this. So wherever you have x, substitute what? H upon r. Okay, wherever you have n, substitute minus 2. Okay, x equals to h upon r, n equals to minus 2, and write this, expand this. Okay, binomially. Then what do we get? We get gh is equal to g multiplied by the binomial expansion of that term, 1 plus h upon r raised to minus 2, which is 1 plus n is minus 2, x is h upon r. So minus 2 multiplied by h upon r plus you have n multiplied by n minus 1 upon 2 factorial. So minus 2 multiplied by minus 2 minus 1, that is minus 3 divided by 2 factorial, that's 2, okay, multiplied by h upon r square, okay, plus so on and so forth up to plus h upon r raised to minus 2. So you write this. Okay, after that, for small heights, so for, you can say, very small heights, h is very small compared to r. H square will be very small compared to r square, right? H square will be very small compared to r square. Okay, then you neglect all terms after this. Okay, you neglect all terms after this point, and you will be left with 1 minus 2h divided by r only. So then, okay, you have gh equals to g multiplied by 1 minus 2h upon r only. Okay, but when is this formula valid? When is this formula valid? So this formula is valid when h is very small compared to r. Okay, I mean, see, r is equal to how much is the radius of earth? It is 6,400 kilometers. Okay, so you can say up to 10% of this height, up to 10% of this height, this approximation will give you a correct result. Okay, after that it will not be valid, or it will not be a good approximation. So see, you have got two formulae. Okay, you have got two formulae for acceleration due to gravity at height h. One is this formula, it is g times r plus h. Sorry, it is gh is equal to g multiplied by r upon r plus h square. This is the correct formula. It is valid anytime. Okay, this is valid in all cases. Okay, whether height is small, whether height is large, doesn't matter. This is valid everywhere. Okay, but if height is small, 5 kilometers, 10 kilometers, okay, small meaning small compared to the radius of earth. So if height is small, then you have this another formula, gh is equal to g multiplied by 1 minus twice h upon r. So this is valid only for small heights. Okay, so for 5 kilometers, 10 kilometers, 50 kilometers, okay, 100 kilometers, you can say, right? After that, as height goes on increasing, this formula will become it won't be that much correct. Okay, so it will start giving you the results which are not correct. Okay, which are not good. So in an exam, you can use this formula for let's say up to 10% of the height. Okay, so when h is up to 10%, okay, how much is 10%? 640 kilometers. So till that much height, it will still give you fairly good results. After that, the results won't be good. So is it clear in what case, what formula to use? So we found acceleration due to gravity at height h above the Earth's surface. Now we'll find out the formula for acceleration due to gravity at depth d below the Earth's surface. Okay, so we found an expression for the acceleration due to gravity above the Earth's surface. Now what we will do is we will imagine a well. Okay, so we'll dig a well inside Earth, and okay, the well is deep, right? So we are going to this point at depth d below the Earth's surface. And suppose somebody goes here, then what will happen? How much will be the value of acceleration due to gravity? Okay, this is what we have to find out. All right. Okay. So how much would be this distance then? If this distance is r, this much distance will be equal to what? R minus d. Right. This much distance is r minus d. Okay. So now what will be the value of acceleration due to gravity over here? Okay. At depth d. That's what we have to find out. So now, okay. See, if we have a spherical shell, so we studied about this yesterday. If we have a spherical shell, okay, what is the value of acceleration due to gravity, or what is the value of gravitational force inside that spherical shell? Zero, right? So inside the spherical shell, the acceleration due to gravity is zero. Okay, so now when you consider mass which is at depth d below the Earth's surface, now acceleration due to gravity on that mass due to this part of the Earth, okay, due to this part of the Earth will be equal to zero, because you can think of this part as made up of n number of shells like this, one inside other. Okay, we can think of this part. Okay, we can think of this part like this. Okay, it is made up of n number of shells. So acceleration due to gravity over here due to all these shells will be equal to what? Zero. Okay, so if you go till depth d, the acceleration due to gravity at that point, it is contributed by only this much part. Okay, only this much part. Okay, and the acceleration or the gravitational force due to outside outside part will be equal to zero. Okay, so if you go here, the gravitational force due to this part will be equal to zero. Okay, so only this part, only this part will exert the gravitational force. Is the point clear? Okay, so now see, what is the formula for acceleration due to gravity? G is equal to gm over r square, right? Now the mass can be written in terms of density and volume. Okay, sorry. So we know, if let's suppose rho is density of earth. Okay, now you will say the density is not constant, right? So earth is not uniform. Okay, there are different materials. Now on earth's surface itself, in some part there is land. It is made up of various rocks. Okay, the soil of different kinds. Okay, so the density is not constant. Okay, then there is water also inside the earth's surface. Okay, inside the earth crust there are various metals. Okay, I'm sorry. So that things are there. So what we are talking about is the mean density, average density of earth. Okay, so what is rho? It is average density, right? So it is density of earth. So we know density equals to mass upon volume. Therefore mass can be written as density multiplied by volume. And what is volume of a sphere? So volume of a sphere is 4 by 3 pi r cube, right? Volume of a sphere is 4 by 3 pi r cube. So we can substitute this thing in place of this mass. So what do we get? The acceleration due to gravity on Earth's surface. Due to gravity on Earth's surface. Okay. G is equal to G upon R square multiplied by this thing. M is this thing. Rho multiplied by 4 by 3 pi r cube. So let's substitute that. So it is rho multiplied by 4 by 3 pi r cube. Okay, so here you can divide this r cube by r raised to 2. So r will be left. Okay, and therefore what do we get? We get 4 by 3, okay, pi multiplied by r multiplied by rho multiplied by capital G. So this is the formula for acceleration due to gravity in terms of mean density, average density of earth. Okay, and this formula also is an important formula. Sorry, this formula is also an important formula. Now check this formula. So what are the constants in this formula and what are the variables? So pi is constant, right? Rho is constant, G is constant, and if we talk about earth, okay, R is also constant. Okay, so for the sphere of the size of earth, R is also constant, right? For earth it is constant. Now if we think about this much sphere only, if we think about only this much sphere, then what will be value of this r? It will be r minus d. Okay, what is radius of this sphere? It is r minus d. Okay, so mean density will consider it to be constant. G is constant, right? So what is only one variable for this sphere? It is the radius, and radius of this sphere is r minus d. Okay, so we'll substitute that. So we get acceleration due to gravity at depth d is equal, okay, G suffix d, and it is what? 4 by 3, we have pi multiplied by r is radius is r minus d multiplied by rho into G. Okay, right? And then what we can do is, again, just like what we did in case of acceleration due to gravity at some height, we'll do the same thing for the depth also. Okay, so we'll divide this by acceleration due to gravity on Earth's surface. Okay, so sorry, so let's divide by G. Okay, so it is 4 by 3 pi r rho g, and everything gets cancelled except for r minus d upon r, right? Everything else gets cancelled out. So you have g at depth d divided by g on Earth's surface equals to r minus d divided by r. And then you move this g on the other side. Okay, so you get g suffix d is equal to g multiplied by, you can divide this thing by r. So r upon r is 1. Okay, so you have 1 minus d upon r. Okay, so the g multiplied by 1 minus d upon r, right? So you have this formula for the acceleration due to gravity at depth d below the Earth's surface. Okay, and where is this formula valid? Actually, here we didn't use any series expansion, so we didn't do any approximation. This is valid everywhere, right? The only approximation that we did is what? That Earth's density is constant. Okay, and we are calling it as mean density. Okay, so this formula is valid everywhere, but the formula for the height is valid only for small heights, right? Which one? This formula is valid for small heights only, but this formula for the height is also valid for all heights. Okay, so is it clear? Yes, no? Okay. So now, if I'm sorry, if I want to plot acceleration due to gravity versus the distance. Okay, acceleration due to gravity versus distance. So you can see in this formula, if you see this formula, okay, for radius or for depth, okay, for depth d, right? Or let's suppose, okay, see, if you consider this formula, then if you go to some depth, what will change? The radius will change. Okay, radius of the sphere will change. So you have to just change this r. Okay, so if I want to plot the acceleration due to gravity g at some position r versus r itself. So what is r? R is distance of the point from the center of Earth. Okay, r is distance of the point from the center of Earth, right? So now see, below the Earth's surface, this acceleration due to gravity is directly proportional to r. Okay, it is directly proportional to the distance from the center of the Earth, right? So how will the graph look like? It will be a straight line like this below the Earth's surface. After that, okay, after that, so for below the Earth's surface, I can write the formula is g at r is equal to 4 by 3 pi r rho g, where this r is distance from the center of Earth. Okay, then this is still r equals to capital R. This is still what? R equals to capital R. After that, if you have some height, then the formula is gh is equal to g multiplied by r upon r plus h square, or you can say r upon small r square. So in this formula, this g is constant. Okay, acceleration on Earth's surface, we can consider it to be a constant. This r is constant. What is changing? The small r is changing, right? So it is inversely proportional to r square. So as r goes on increasing, okay, the acceleration due to gravity will go on decreasing. So, and how is it decreasing with r? So it is inversely proportional to r square. Okay, so it is falling like this. That's inverse square relation. Okay, so it's something like this. It is falling something like this. Okay, so the variation of acceleration due to gravity versus the distance from center of the earth, that graph will look like this. Is it clear? Okay, there is one more thing. One more thing is gravitational field. Okay, so what is gravitational field? So it is gravitational force acting on any object per unit mass of the object. So what is gravitational field? Gravitational field is equal to, it is defined as the gravitational force acting on any mass divided by mass of the object. So it is gravitational force per unit mass. Okay. So now this gravitational field can be due to n number of objects. Okay. So let's suppose we have n number of masses m1, m2, m3, so on and so forth. Okay. So all of them, they will create their own gravitational field, and the net gravitational field will be vector sum of all of the gravitational fields produced by all of those masses. Okay, so for an example, you keep this mass m over here. This is called as test mass. Okay, so this first mass will pull it towards itself, right? So it will exert some force. You can call it F1 bar. Okay, the second mass, it will exert some force. Call it F2 bar. Okay, third mass, it will also exert some force. It is F3 bar. Okay, it will have some magnitude F3 bar. So resultant of all these vectors, okay, F1 bar, F2 bar, F3 bar, and if there are n number of masses till Fn bar, then resultant of all those forces will give you what? The net gravitational force acting on this mass. Okay, and the net gravitational force divided by this mass is the gravitational field at that point. Okay, so gravitational field at any point in space is the net gravitational force acting on any object divided by mass of the object, which is kept at that point. Okay, so is it clear? Gravitational field is clear. Now, if we have, suppose we have Earth. Okay, so what would be gravitational field due to Earth? So you have some mass, you keep it here. You have some mass. Okay, you are keeping it here. So what will be gravitational field due to Earth only on that mass? It is just the acceleration due to gravity. Okay, because how do we define the gravitational field? It is the gravitational force. Okay, gravitational force divided by mass. Gravitational force per unit mass. And what is force per unit mass? It is just acceleration, gravitational acceleration. Okay, acceleration due to gravity, you can say. Okay, so what is gravitational field due to Earth? So field due to Earth, okay, gravitational field field due to Earth is equal to what? G times m upon r square. This is the force, gravitational force of Earth on that mass divided by that mass. So m and m gets cancelled out. So you get gm upon r square, and that's nothing but the g at height h, you can say. Okay, it is gm upon r square, which is capital R plus h square. So is it clear? Gravitational field due to Earth is just the acceleration due to gravity. Let us solve some previous year questions. Okay, so this is from 2014. Dependence of intensity of gravitational field E of Earth with distance r from the center of Earth is correctly represented by. So gravitational field is nothing but what? Acceleration due to gravity. Okay, tell me which one is correct. I have seen this, no? It's option B. Right, it's option B. Okay, so this is simple question. Next one, which one of the following plots? Okay, so yeah, others, is there a problem in this question? No, right, Sanjay? Okay, good. Then next question, which one of the following plots represents the variation of gravitational field on a particle with distance r due to a thin spherical shell? Now this is different. It is thin spherical shell. Okay, gravitational field due to thin spherical shell of radius r. Small r is measured from the center of spherical shell. So we know this. Okay, for a spherical shell, if you keep a mass inside shell, okay, what is gravitational field? It is gravitational force per unit mass. So let's suppose mass of the shell is capital M. Okay, if you keep other mass inside the shell, what will be the gravitational force on that mass due to the shell? It's zero. Okay, therefore the gravitational field inside the shell is also zero. Till what? Till the distance r. Okay, till you reach till the surface of the shell, right? So when r is smaller than r, E is equal to 0, the gravitational field is equal to 0. When you go outside of the shell, okay, then the gravitational force is equal to what? It is just gmm upon r square. So it is inversely proportional to r square. Okay, therefore the gravitational field, which is force per unit mass, will be just gm upon r square. Okay, therefore E, which is equal to force upon mass, is just gm upon r square, and 1 upon r square is like this. Okay, so which one is correct? Here field is denoted by F. Okay, sorry, it's not E, they are denoting it by F. So let's call this F as the gravitational force, and field F is equal to what? This force divided by mass. Okay. So still it doesn't matter, it's option B. Yes, no. Okay, till the distance from center of the shell is less than r, the force on any mass which is kept inside the shell will be equal to 0. Okay, so therefore the gravitational field is 0. Okay, till distance r. After that, it is equal to gm upon r square. Okay, gm upon gm divided by capital R square. Okay, this will be the maximum value, and then it falls as inversely to the R square. Okay, so it is gm upon R square. So therefore it's option B. Then let's see next question. A body of weight 72 Newton moves from surface of the earth at height half of the radius of earth. Then the gravitational force exerted on it will be. So gravitational force, okay, will be equal to what? At height h is equal to mass multiplied by acceleration due to gravity at that height. Now question is, which formula for acceleration due to gravity should we use? We have this formula, g multiplied by r upon r plus h square, and we have another formula, g multiplied by 1 minus twice h divided by r. So which one should we use in this question? Okay, height is equal to, given is height is equal to half of the radius of earth. First or second, tell me. Second formula is approximate. Okay, we can use it till the time h is very small compared to r. Okay, what do I mean by very small? Max to max 10%. Okay, and here it is half. Okay, h is equal to r upon 2. So we cannot use the second formula. We have to use the first one. Right? Okay. So what is weight of object? It is gravitational force due to earth on an object. Okay, so W is equal to mg. This is on earth surface. Earth surface. And for height h, the weight will be equal to what? Weight at height h will be equal to mass multiplied by acceleration due to gravity at that height. Okay, so m into gh, which is m multiplied by, we'll use this formula. Okay, g multiplied by r upon r plus h whole square. Okay, and what is mg? It is weight on earth surface. So w, let's call it w. So let's put h, so it is r upon r plus r by 2 square, right? So it is 3 by 2 r in denominator, r gets cancelled, it is 3 by 2 in denominator, so we can move that 2 into the numerator. So 2 by 3 square, which is 4 by 9, right? 4 by 9, this is my 9, okay? It's not g, this is 9, multiplied by weight. And how much is weight? It is 72 newtons, 72, okay? So 8 nines are 72, so we have 8 times 4, 32 Newton is the answer. Oh, you calculated? Very good. Okay, it's option B. Good. If the mass of Sun were 10 times smaller and the universal gravitational constant were 10 times larger in magnitude. Okay, which of the following is not correct? Option A, raindrops will fall faster. Option B, walking on ground would become more difficult. Option C, time period of simple pendulum on Earth would decrease. And option D, G on Earth will not change. Can you tell me? Mass of Sun were 10 times smaller. Okay. So mass of Sun is 10 times smaller and G is 10 times larger. So let's suppose G dash is equal to 10 times of I'm sorry, G. Okay, and mass of Sun is equal to 1/10 of the current mass of Sun. So ms prime is equal to ms divided by 10. So raindrops will fall faster. Okay, will this happen? Yes, it will happen, because what is acceleration due to gravity? It is gm upon r square. Now you have if G changes, okay, if capital G changes, what will happen? Small g will also change. Now mass of Earth is not changing, radius of Earth is not changing, okay, so they are given to be constants. So it is G prime upon multiplied by m divided by r square. Okay, so now see, G prime is 10 times of G, so that means acceleration due to gravity will become 10 times, okay, 10 times larger. So raindrops will fall faster because Earth is attracting them with greater magnitude, 10 times greater magnitude, right? So V, which is square root of 2gh, right? If they are falling from some height h, the square root of 2gh. So since g is increasing, V will increase. So this is true. Then walking on ground would become more difficult. This is also true because acceleration due to gravity has increased. So we have to exert more force against Earth's gravitational pull, right? So this will become more difficult. It is true. Time period of simple pendulum on Earth would decrease. So what is time period of simple pendulum? T is equal to 2 pi square root of L upon G. Okay. So it is inversely proportional to root G. So if G increases, T decreases, right? If G increases, T decreases. So this is true, this is true, this is true. Which is not true? This is not true, right? And we can see that G on Earth will not change. They are saying G will not change, small g, acceleration due to gravity. And okay, so it will change, right? So this is the answer. Let's see next question. A spherical planet has mass m suffix p and diameter d suffix p. A particle of mass m falling freely near the surface of this planet will experience an acceleration due to gravity equal to. So very simple question, right? So we just have to remember G equals to G times m upon r square. So for that planet, what will be G? Gp will be G into mp upon rp square. Okay, radius of that planet square. Okay, right? So here diameter is given, which is radius divided by 2. So we can substitute that. So we get G times mp, mass of the planet, divided by diameter, radius is diameter upon 2. So dp by 2 square. Okay, and that 2 square will go to the numerator. So you can say it is 4 times g multiplied by mass of the planet upon dp square. Okay, so this is it's option A, right? This is very simple. Next question is, imagine a new planet having the same density as that of Earth, but it is 3 times bigger than the Earth in size. Okay, let's imagine a new planet. Okay, same density as that of Earth, and it is 3 times bigger than that of Earth. If the acceleration due to gravity on the surface of Earth is g, and that of the surface of new planet is g dash, then tell me, see, if density is coming, which formula should we use? G is equal to 4 by 3 pi r rho g. Okay, so I wrote this formula for Earth. For that planet, it will be g dash equals to 4 by 3 pi r dash rho dash. Okay, this g will not change. It is universal gravitational constant, right? So density of that planet is equal to density of Earth. Okay, so g for Earth is 4 by 3 pi r rho times g. So rho dash is equal to rho. It's given, but it is 3 times bigger. Okay, so r dash is equal to 3 times r, right? And therefore, you can say, you can write here 3 times r, it is 4 by 3 pi multiplied by 3 times r into rho into g. Rho dash is equal to rho. R dash is equal to 3 times r. and therefore it is 3 times of g, right? It is equal to 3 times of g. Option D. Okay, so whenever density comes, okay, whenever density is involved, you have to use this formula. Okay, please remember this. Whenever density is there, use this formula. Okay. Next question. The density of a newly discovered planet. Again, newly discovered planet. Okay, planet is newly discovered. Is twice that of Earth. Acceleration due to gravity at the surface of the planet is equal to that of the surface of Earth. If the radius of Earth is r, the radius of the planet would be. Okay, so newly discovered planet. G dash is equal to g. This is given. Okay, so 4 by 3 density is involved. Which formula do we have to use? 4 by 3 pi r rho g. Okay, pi r rho multiplied by capital G. But it is for that planet, so let's put dash r dash rho dash. Okay, it's equal to density of, sorry, acceleration due to gravity of Earth. It is 4 by 3 pi r rho g. So 4 by 3 pi, 4 by 3 pi cancelled. G and G is cancelled. So what's given? Radius, sorry, density is given is twice that of Earth. Okay, so rho dash is equal to 2 times rho. Rho dash is equal to 2 times rho. So rho and rho is also cancelled, right? I will just put rho dash is equal to 2 times rho. So you get r dash is equal to what? R upon 2. Take the 2 on other side, right? So questions on gravitation. Most of the questions are very simple. The acceleration due to gravity on a planet A is 9 times the acceleration due to gravity on planet B. Okay. A man jumps to height 2 meters on surface of A. What is the height of jump by the same person on planet B? Yes, can you tell? So here, now same man, suppose same man jumps with same velocity, right, on both the planets. So till what height will he go? Okay, so acceleration on a planet A is 9 times the acceleration due to gravity on planet B. Okay, so we know that V square is equal to 2gh. Okay, so V A square is equal to 2 times G A H A. Okay, and we'll divide that by VB square, which is 2 times GB HB. Okay, but same man will jump with same velocity, right? So V square and V square is cancelled. We can write 2 times GAHA is equal to 2 times GB HB, right? Or GAHA is equal to GB HB. Okay, so right. So what will be the answer? So on planet A, it is 9 times. Man jumps to height of 2 meter on surface of A. So this is 2. HA is 2. Okay. And GA is 9 times of GB multiplied by 2 we have. Okay. So it is GB times HB. So this H and H, HB and HB gets cancelled. What did I do? Sorry. GB and GB gets cancelled. Okay. So HB is equal to what? 9 times of 2. That's 18 meters. Next question. What will be the formula of mass of Earth in terms of small g, r and g? This is very simple, right? So we just have to remember g is equal to gm upon r square. Okay, so what is asked? What is the formula for mass? So what is the formula? M is equal to g multiplied by r square. divided by capital G. Okay, it is option B. The acceleration due to gravity G and mean density of Earth rho are related by which of the following relations? So we know that relation, okay, but they have asked about rho, not G. Okay, so we know that G is equal to 4 by 3 pi r rho G, right? And we want rho because in all options they have given rho. So take everything else on the other side. So rho is equal to, okay, 3 by 4 times G. Okay, if I take this on other side, it will become 3 by 4 times G divided by pi r capital G divided by pi r capital G, which is the which option? Option A, right? Option is answer. Okay, this is straightforward. All right. Next question. Radius of Earth is about 6,400 kilometers and that of Mars is 3,200 kilometers. The mass of Earth is about 10 times mass of Mars. Okay, so radius of Mars Mars is equal to what? Half of the radius of Earth, r upon 2 we can say, and mass of Earth is about 10 times mass of Mars. Okay, that means mass of the Mars is equal to mass of Earth divided by 10 because Earth's mass is 10 times. Then an object weighs 200 Newton on the surface of Earth. Its weight on the surface of Mars will be. So what we have to do? We have to find out the acceleration due to gravity on surface of Mars. Okay, so let's do that. So G on Mars surface will be equal to G times mass of the Mars divided by radius of Mars square. Okay, and that is G times what is mass of Mars? It is mass of Earth divided by 10, m upon 10 divided by, and what is radius of Mars? It is radius of Earth upon 2. So it is r upon 2 square we have. Okay, so it is 2 square is 4. It will go to the numerator. So you have 4 upon 10 times gm upon r square. Okay, that is 4 by 10 or 2 by 5 times the acceleration due to gravity due to the earth. This is acceleration due to gravity due to earth. Okay, so it is 2 by 5 times g, and therefore weight on Mars will be equal to what? 2 by 5 times weight on the earth. Okay, and what is weight on earth? It is 200 Newton. Okay, so 2 by 5 multiplied by 200. How much is that? 2 by 5 multiplied by 200. So 200 by 5 is 40. 40 times 2 is 80. So 80 is the answer. Got it? Oh, you solved it. Very good. Okay, correct. Option C. Okay, let's see next question. A body weighs 72 Newton on surface of Earth. What is gravitational force on it at the height equal to half of the radius of Earth? So this is repeated question, exactly repeated, right? So we have solved it. It is 32 Newton. I remember. Yes, no? The body weighs 200 Newton on surface of Earth. How much will it weight? Halfway down to the center of Earth. Okay. So for that we need to find acceleration due to gravity at depth d. And how much is d? It is r by 2 because they are asking how much will be its weight halfway down to the center of Earth. That means d is equal to r upon 2. So GD is equal to G multiplied by 1 minus d by r. And what is d by r? If you take r on other side, so d by r is 1 by 2. 1 minus 1 by 2 is 1 by 2. So it is G by 2 only. Okay, G by 2. And since acceleration due to gravity becomes half, weight becomes half because weight is m times g. Okay, so it is 100 newtons. Next one, the acceleration due to gravity at height 1 kilometer above the earth is same as a depth d below the surface of earth. Then how much is d? They are asking. So here it's only 1 kilometer, so we can use this formula. G at height h is equal to G multiplied by 1 minus twice h upon r. Okay, and they are saying same as depth d, so it's equal to GD. So what is GD? GH is equal to, they are saying GH is equal to GD. So it is equal to what? G multiplied by 1 minus d upon r. So this G and G gets cancelled. Okay, after that it is 1 minus twice h upon r is equal to 1 minus d by r. So that is twice h upon r is equal to d by r. R gets cancelled. D is equal to 2 times h. Okay, so it is 2 kilometers, right? D is equal to 2 times h. H is equal to 1 kilometer. So D is equal to 2 kilometers. Okay, simple question. And this question has been repeated many times. Starting from center of earth having radius r, the variation of g, acceleration due to gravity, is shown by. Okay, sometimes they call it gravitational field. So it's same thing. What is the answer? It's option B. Okay, good. Then next question. The height at which weight of body becomes 1 by 16th is weight on the surface of earth. So this is also simple. So what they mean is GH is equal to 1 by 16th of G. Okay, but we know GH is equal to G multiplied by what? Okay, because it becomes 1 by 16, so we have to use this formula. It will not happen for small heights, right? So r upon r plus h square. Okay, GH is G multiplied by r upon r plus h square. So it is 1 by 16th of G. G and G gets cancelled. Then we have to take square root. Okay, so r upon r plus h square is 1 by 16. That means r upon r plus h is equal to 1 by 4. That means r plus h is equal to 4r. Okay, so h is equal to what? 4r minus r, that is 3r. Then this is from mains 2010. Okay, and its answer is option 4, that is A. So it is repeated many times, repeated in many exams, this question. Okay,